Okay, I just wanted to make a quick video going over a few problems that we had for our homework that you guys turned in to me to kind of clear up a few things. So first off, you'll bear with me because I have the book with me to read the problems. In section 4.1, you had to do number 122, and it says, as the fan, which I drew there, it's in your book, but I drew it right there, as the fan rotates, which point A or B has a greater angular speed, which point has a greater linear speed? And if you remember in the other video we did, we said angular speed was the speed at which the angle changes. Linear speed is the regular speed that we're used to. It's just change in distance over change in time. So for the sake of argument, if this is my fan, and I'll draw a line right through those 2 points, if, say, I want to calculate the speed until the fan blade goes down here, that's my theta right there. For angular speed, we just calculate how quickly this angle changes over time. But both points form the exact same angle, which means both of them are going to change at the exact same angular speed because they're going through the exact same angle. So where they are on the fan blade doesn't matter. They both have the same angle associated with them, so their angular speeds are equal. Their linear speed is change in position. So essentially, if I can kind of draw this, it's going to be circular. So A will go to there, B will go to here. As the fan blade rotates, well, in the same amount of time, this blade goes from here to here. A goes this distance, B goes this distance. And clearly, if they both go those distances in the same time, B has to travel further, so B has a greater linear speed. Angular speeds are the same, linear speeds change because the points are on different places. The next problem, 123. If an angle of a sector is held constant, but the radius is doubled, how will the arc length of the sector and area of the sector be affected? And one thing I would point out, I know the work you do in ALEKS is a lot of computational type work, so because of that, a lot of the problems I give you from the book to do will be more theoretical thinking math type problems to get you ready for calculus and stuff like that, to make you think about what's going on. But the one thing you can do is draw a picture. Draw a picture and maybe make up your own numbers. See what happens when you use numbers that you know and kind of use that to see what's actually happening in general. So for the sake of argument, let's see, we have a circle. And we'll say the radius equals 4. Then let's see, for number 123, if an angle of a sector is held constant but the radius is doubled, how will the arc length and area of the sector be affected? So I'll pick an angle. I'll pick a nice angle. We'll go with 90 degrees. And we said my radius is 4. So then what do I care about? Arc length and area of the sector? Well, for this original triangle, the original circle right here, what's the arc length? S equals r theta. So let's see, r is 4, theta 90 degrees. We have to do that in radians, which is pi over 2. That's 4 pi over 2, which is just 2 pi. So the arc length is 2 pi. What about the area of the sector? Well, the area of the circle is pi r squared. Let's see, that's pi, my radius is 4, so that's 16 pi. But that's the whole circle. I only want 1/4 of it. So just divide that area by 4 and I get 4 pi. So now I have the arc length and area of the sector for this circle. Now do what the problem says. If the angle is held constant, but the radius is doubled, so okay, now pretend my radius, instead of being 4, pretend it's 8. What happens? Well, let's see, S is r theta. Now it's 8, my radius, times theta, which is pi over 2. I'm sorry, it's pi over 4. Pi over 2, my bad. And that simplifies to 8 pi over 2, which is 4 pi. For the area of the sector, area equals pi r squared. So that's pi. Now my radius is 8. So 8 squared is 64. So it's 64 pi, but again, that's only 1/4 of the circle. So we divide that by 4. 64 divided by 4 is 16 pi. Now actually see what's going on. In terms of the arc length, it was 2 pi, and when I doubled the radius, it became 4 pi. So it looks like if I keep the angle the same but double the radius, the arc length doubles. In terms of math speak, from 171, you guys remember things being directly proportional, directly varying directly, varying inversely, things like that. For this equation right here, S and R vary directly, which essentially means that if this doubles, S doubles. We doubled R, S will get doubled too, and that's what happens. In terms of sector, it was 4 pi, now it's 16 pi. Well, it didn't double, it actually multiplied by 4, which means it quadrupled. And again, the idea is similar in terms of variation. Well, now these things are related, not directly, but this is actually squared, which results in everything getting quadrupled when you double the radius. It gets factored in twice, essentially. So there we go. Again, I'm going to give you problems where you have to kind of think about what's going on. If you're a little confused, you can just make up your own numbers, make nice round numbers, solve the problem out, look at your solutions, and then from there try to draw a conclusion. Here it was pretty obvious. 2 pi became 4 pi, 4 pi became 16 pi. I can also upload notes of actually written solutions to all these homework problems. I have no problem doing notes or videos, whatever helps you guys best, so just let me know. Post it in the discussion board, send me an email, whatever. But anything to help you. And in the future, if you're working on the homework and you have a question, feel free to email me or just say, hey, I have no idea how to solve number 64. And when I have time, I'll make a quick video, throw it up on YouTube so you guys can see it.